So let's say that I have a vial of some mystery liquid right over here, and I want to start figuring out what's going on there. And the first step is to think about, is it just one substance or is it a mixture of multiple substances? And the focus of this video is a technique to separate out the substances, to understand at least how many there are, based on their polarities. And this technique generally is called chromatography, but we'll focus on thin layer chromatography, which is the most common that you might see. But other variations of chromatography, like paper chromatography, operate on very similar principles. So what we're going to do is set up on top of something like glass or plastic, we're going to put a thin layer of a solid polar substance. Now what you typically do is put a thin layer of silica gel. That's the most common solid polar substance that folks use. And it's also porous. And the fact that it's porous is really important because we're going to want liquid to have capillary action and travel up through it. Now the silica gel, as I mentioned, this thing is very polar. Now what you're going to do is take some of our mystery substance, let's say it's this color right over here, and we're going to place a dot of it on that silica gel. You then want to take this plate that has the silica gel on it and that little dot of our mystery substance, and then you want to dip just one end of it in a solution. And what's really important is that the solution is less polar than the silica gel. Less polar here. And we'll talk a little bit about what happens depending on how polar this is. Now usually this is going to be a very shallow amount of this solution, which as we'll see will be something of a solvent. And you usually want to put it in a closed container like this so that this fluid down here doesn't evaporate out. And then what do you think is going to happen? Well, as I mentioned, this is a porous substance here, and so you're going to have capillary action. This fluid at the bottom is going to move upwards through the silica gel, through those little pores in the silica gel. This is the stationary phase. Why do we call it that? Well, because it's not moving. And you can imagine we would call this less polar solvent the mobile phase, because that is traveling through the silica gel. And it's picking up some of this mystery substance and it's transporting it. And let's say this mystery substance is made up of two different things. If something is more polar, that means it's going to be more attracted to the stationary phase, which is very polar. And so it's not going to travel that far. While the parts of our mystery substance that are less polar, they're not going to be attracted to the silica gel as much. So they're going to travel further with the solvent. So maybe it might go like that. And you would run this until your mobile phase makes a good way to the top of your silica gel right over here. Now just looking at this, and the reason why it was called chromatography is when they originally did this, they were actually separating out various tissues in vegetation that had different colors. And though chroma is referring to the various colors, but it doesn't necessarily even have to refer to things that have different colors, or sometimes you might need a UV light to see them. But when you run thin layer chromatography, you will see that your original dot will have traveled to various degrees with your solvent and then will now be multiple dots depending on how many things were in your original mixture. And as I just mentioned, this thing right over here, this is the less polar thing, is going to travel further than the more polar thing, more polar constituent substance, because the more polar thing is more attracted to the silica gel, which is stationary. And there is a way to quantify how far these things traveled relative to your solvent. And that's called a retention factor. Retention factor, which the shorthand is R subscript F. And it's just defined as the distance traveled by the solute divided by, and you might guess this, the distance traveled by the solvent. Traveled by solvent. And so let's call this substance A, and let's call this up here substance B. And let's say we get a ruler out. Well, if we wanted to calculate the retention factor for substance A, what would it be? Pause this video and think about it. Well, it looks like our solute from its starting point traveled about 1 centimeter. So 1 centimeter over how far did our solvent travel? Well, our solvent started over here, and the front of the solvent looks like it traveled 10 centimeters. So I'd put it over 10 centimeters. So this is going to be a retention factor for substance A of 0.1. Similarly, what is going to be the retention factor for substance B? Pause this video and try to calculate that. Well, it looks like it would have traveled from 1 centimeter to 2, 3, 4, 5, 6. So it travels 5 centimeters. And once again, the front of the solvent traveled 10 centimeters. And so you get a retention factor here of 0.5. Now let me ask you an interesting question. What would happen if we were to run this again with the same mystery substance, with the same silica gel stationary phase, but we were to replace the solvent here? We would replace the mobile phase with something more polar. So a more polar mobile phase. What would happen then to the retention factors? Well, if it's more polar, its polarity is going to compete more with the polarity of the stationary phase, and so it's going to be able to pull things further. So this would cause the retention factor to go up.